Welcome to WikiPodcast. Imagine looking at everything around you, your coffee cup, maybe the air you breathe, even the stars way out there in the night sky. What if I told you all of it, every single thing, visible or not, is built from just a tiny handful of fundamental ingredients? Today we're embarking on a deep dive into the standard model of particle physics. You might hear it called nature's building blocks or even the universe's ultimate periodic table. Our mission is pretty clear. We're going to unpack what it is, what pieces it actually includes, how it explains the forces shaping our reality, and maybe even more fascinating, what profound mysteries it doesn't solve yet. So get ready to go small, really, really small, and maybe see the universe in a whole new way. Okay, let's unpack this then. When we talk about the standard model, what exactly is it? How does it map out this micro-universe?
Right. Well, it's essentially our most comprehensive theory right now. It describes three of the four fundamental forces we know. That's the electromagnetic, the weak, and the strong interactions. And crucially, it also classifies all the known elementary particles, the ones that make up matter and the ones that carry these forces.
So it's like a grand organizational chart for everything tiny.
Exactly. Think of it like the best instruction manual we have for how the universe works at its most basic level. Components, interactions, it's all laid out.
How long has this manual been around?
It wasn't just, discovered overnight. It was developed in stages really throughout the latter half of the 20th century, a huge collaborative effort. Its current form was pretty much finalized in the mid-1970s. And since then, experimental confirmations have just kept rolling in, adding immense credibility.
Confirmations like what?
Well, things like predicting weak neutral currents, finding the W and Z bosons, then later discovering the top quark in '95, the tau neutrino in 2000, and of course the really big one, the Higgs boson, in 2012.
The Higgs. We'll definitely have to talk about that.
Absolutely. Each discovery wasn't just finding a missing piece, it confirmed the whole underlying structure. It's a remarkable triumph of modern physics, really. It forms the basis for so much of our understanding and even for building more exotic models beyond it.
Okay, so it's an incredible achievement. Let's get into the details. If this is our map, what are the actual building blocks made of? What are these particles?
Right. So the heart of it, you have 12 elementary particles called fermions. These are the particles that make up all the actual stuff, the matter we observe.
Fermions. Okay.
They have a specific quantum property called spin 12, technically, and they follow something called the Pauli exclusion principle.
Pauli exclusion. Sounds important.
Oh, it's fundamental. It basically says no two identical fermions can be in the exact same quantum state at the same time. That's why atoms have structure, why matter takes up space, why you can't just walk through a wall.
Got it. So that's why things are solid.
Pretty much. And importantly, each fermion also has a corresponding antiparticle. Same mass, but opposite charge, like a mirror image.
Interesting. So 12 fermions. How are they organized? You mentioned groups?
Yes, we classify them into two main groups, quarks and leptons. And within each of those groups, there are three generations.
Generations. Like families?
Sort of, yeah. Each generation is basically a heavier version of the previous one. Let's start with quarks. There are 6 types, or flavors, as physicists like to call them.
Flavors. Okay.
Up, down, charm, strange, top, and bottom. Now, the really fascinating thing about quarks is that they carry something called color charge.
Color charge. You mentioned that earlier. Does that mean they have actual colors?
No, not literal colors like red or blue. It's just a name for a type of charge related to the strong nuclear force, the force that holds the nucleus of an atom together.
Ah, the strong force. Okay.
And this property leads to something really weird called color confinement.
Color confinement. What does that mean for us practically?
It means you can never find a quark all by itself, ever. The strong force is so strong at larger distances, it's like an unbreakable rubber band. Quarks are always bound together in groups to form color-neutral composite particles. We call these hadrons.
Hadrons. Okay, I've heard that term.
There are 2 main types, mesons, which are made of 1 quark and 1 antiquark pair, and baryons, which are made of 3 quarks. And the most famous baryons, the ones you definitely know, are the proton and the neutron, the building blocks of atomic nuclei.
Protons and neutrons, made of quarks. Wow.
Yep, 3 quarks each. And because quarks also carry electric charge and another property called weak isospin, they also interact via the electromagnetic and weak forces too. They're quite sociable particles.
Okay, so that's quarks. What about the other group, the leptons?
Right, the leptons. There are 6 of these too. You have the electron, which is very familiar, and then 2 heavier versions, the muon and the tau. And each of those has a partner particle called a neutrino. So there's the electron neutrino, the muon neutrino, and the tau neutrino.
Neutrinos, the ghost particles.
Exactly. The key difference from quarks is that leptons don't carry color charge, so they completely ignore the strong force.
Ah, okay.
The charged ones, electron, muon, tau, interact electromagnetically, obviously, but the neutrinos, they have no electric charge.
Which makes them hard to find.
Incredibly hard. Their motion is really only affected by the weak force and gravity. They can pass through, well, pretty much anything, planets, stars, without interacting. Detecting them requires massive, very sensitive experiments.
So back to these generations you mentioned for both quarks and leptons.
Yes. The first generation, that's the up and down quarks, the electron and the electron neutrino, these are the stable ones. They make up basically all the ordinary matter we see around us every day. Your coffee cup, the air, us.
So generation 1 is normal stuff.
Pretty much. The second and third generations, charm-strange quarks, top-bottom quarks, muons, tassus, and their neutrinos are much, much heavier. They only show up in really high-energy situations, like in particle accelerators or when cosmic rays hit the atmosphere, and they decay extremely quickly into the lighter first-generation particles.
So they're like exotic, short-lived cousins.
That's a good way to put it. They give us clues about the rules of the universe, but they don't stick around.
Okay, so we have the matter particles, the fermions, quarks, and leptons. Check. Now, how do they actually talk to each other? You mentioned the forces.
Right? That's where the bosons come in. These are the other main class of particles in the standard model. They are the force carriers.
Force carriers.
Yeah, like messengers. Exactly. They mediate the fundamental interactions. They have integer spin, unlike the fermions' half-integer spin. And a key difference is that bosons don't obey the Pauli exclusion principle. You can pile lots of them into the same state, which is basically how forces can build up and spread out.
Okay, so who are the messengers?
Well, first up, the most familiar one, perhaps, the photon.
Light.
Yep, the particle of light. Photons carry the electromagnetic force. They're massless, and they're responsible for all interactions between electrically charged particles. So electricity, magnetism, chemistry, holding atoms together in molecule. No photons, no chemistry, no life as we know it.
Pretty important then.
Absolutely essential. Then you have the gluons.
Gluons. Related to glue.
Precisely. They carry the strong interaction, the force that glues quarks together inside protons and neutrons and holds the nucleus together. There are 8 different types of gluons, and here's where it gets really interesting, and different from photons.
Okay.
Unlike photons, gluons themselves carry the color charge of the strong force.
Wait, the messengers carry the charge they're messaging about?
Exactly, which means gluons can interact directly with each other. This self-interaction is why the strong force behaves so strangely. It gets weaker at very short distances, very high energies. That's called asymptotic freedom. But it gets incredibly strong as you try to pull quarks apart. That's the color confinement we talked about. It's completely different from electromagnetism because of this gluon self-interaction.
Wow, okay. That's complex. So photons for electromagnetism, gluons for the strong force. What about the weak force?
For the weak force, we have the W and Z bosons. These mediate the weak interactions.
And the weak force is responsible for?
Things like radioactive decay, beta decay specifically, where a neutron turns into a proton. It's crucial for processes where particles actually change their identity, their flavor, like a down quark changing into an up quark.
Particle transformation.
Right. Now, the W and Z bosons are unique among the force carriers because they are massive. They have significant mass.
Unlike the massless photon and gluon.
Correct. And their mass is the reason the weak force is so incredibly short range. It basically only operates inside the atomic nucleus.
So the mass limits its reach.
Precisely. The W bosons come in positively and negatively charged versions, W plus and W, and they change particle flavor during interactions. The Z boson is electrically neutral and doesn't change flavor in the same way. And interestingly, at very high energies, the electromagnetic force and the weak force actually unify into a single electroweak interaction. The photon, W, and Z are all sort of aspects of this deeper, unified force.
Fascinating. So forces unify. Okay, we have matter particles, fermions, and force particles, bosons. But you mentioned the W and Z are massive. And the fermions, the matter particles, they definitely have mass. Where does mass itself come from in this picture?
Ah, yes. The million-dollar question, or perhaps $1 billion given the experiments, that brings us finally to the Higgs boson.
The famous Higgs boson. Found relatively recently, right?
That's right. It was theorized way back in 1964 by several physicists, including Peter Higgs, as a necessary piece to make the whole mathematical structure of the Standard Model work, especially the electroweak part. But it wasn't experimentally confirmed until 2012 at the Large Hadron Collider at CERN.
So what makes the Higgs so special?
It's unique. It's a scalar particle, meaning it has zero intrinsic spin. All the fermions have spin 12, the force carriers have spin 1, the Higgs has spin 0. It's fundamentally different.
Okay, spin 0. And how does that relate to mass? What's the mechanism?
So the Higgs boson is an excitation, a particle, of the underlying Higgs field. This field, unlike, say, an electric field that needs a charge to exist, the Higgs field is thought to permeate all of space. It has a non-zero value everywhere, even in a vacuum.
It's just there.
Everywhere.
According to the theory, yes. Think of it like cosmic molasses or maybe a crowded room. As particles move through this field, they interact with it.
Okay.
The more strongly a particle interacts with the Higgs field, the more drag or resistance it experiences as it tries to accelerate. And that resistance to acceleration is what we perceive as mass or inertia.
So particles aren't given mass by the Higgs boson, but they acquire mass by interacting with the Higgs field. Exactly. Different particles interact with different strengths. The photon, for example, doesn't interact with the Higgs field at all, so it has zero mass. The top quark interacts very strongly, making it incredibly massive. The W and Z bosons get their mass through this mechanism, too.
And the electron gets its mass this way.
Yes, electrons, muons, TAS, all the quarks. Their masses come from interacting with this pervasive Higgs field. It was a brilliant theoretical solution that tied everything together and explained why the force carriers for the weak force are massive while the photon isn't.
Wow. Okay, so the Standard Model with fermions, bosons, and the Higgs field, it really sounds incredibly successful. Predicting particles, explaining forces, explaining mass. Seems like we've got it all figured out.
It is incredibly successful. Probably the most successful scientific theory humans have ever devised in terms of its predictive power and experimental verification. But...
And it's a big but.
I sensed that coming. It's not the complete picture. Definitely not. While it's had just immense success, it is absolutely not a complete theory of everything. There are major fundamental physical phenomena out there that it simply doesn't explain.
Like cracks in the foundation.
You could say that. Or maybe entire missing rooms in the house. These gaps are what drive physicists to look for theories beyond the Standard Model.
Okay, so what are these big, glaring omissions? What keeps physicists searching?
Well, the most obvious one, maybe the biggest elephant in the room, is gravity.
Gravity. The force we experience every single second.
That's the one. It's arguably the most familiar fundamental force, but the Standard Model doesn't include it at all.
How can that be?
We have Einstein's theory of general relativity, which describes gravity beautifully on large scales, planets, stars, galaxies, but it's a classical theory. Trying to merge it with the quantum mechanics of the Standard Model at the particle level, well, it just hasn't worked consistently yet. We expect there should be a quantum force carrier for gravity, the hypothetical graviton, but it hasn't been observed, and the Standard Model framework doesn't naturally accommodate it. Finding a theory of quantum gravity is perhaps the biggest goal in fundamental physics.
Wow. Okay, leaving out gravity is huge. What else is missing?
Well, related to gravity and cosmology, the Standard Model has absolutely nothing to say about dark matter and dark energy.
Which make up most of the universe, right?
About 95% of the universe's energy density, according to our best cosmological measurements. Dark matter provides the extra gravity needed to hold galaxies together, and dark energy is driving the accelerated expansion of the universe. The Standard Model contains no particles that have the right properties to be the dark matter we observe. It's made of something else entirely. Something not on our list of 12 fermions and 4 force carriers plus the Higgs.
So 95% of the universe is literally off the map of the Standard Model.
Pretty much, and there's more. It also doesn't fully explain the matter-antimatter asymmetry.
Meaning why there's so much stuff matter and so little antimatter?
Exactly. The Big Bang should have created equal amounts. If it had stayed that way, matter and antimatter would have annihilated each other, leaving just energy. No stars, no planets, no us. The Standard Model has mechanisms for asymmetry, but not nearly enough to explain the universe we see.
That's fundamental to our existence.
Absolutely. And another thing, a crack that appeared after the model was finalized, neutrino masses.
Right, you mentioned neutrinos. The original model didn't predict they had mass.
Correct. In the classic Standard Model, neutrinos were massless, like the photon. But experiments, particularly observing neutrino oscillations, neutrinos changing from one type to another as they travel, have definitively shown they do have tiny but non-zero masses.
So the model had to be patched.
Essentially, yes. The model can be modified to include neutrino masses, but it's not elegant. It requires adding new parameters, new assumptions, pointing towards physics beyond its original scope. In fact, this relates to a broader critique. The standard model relies on about 19 numerical constants, particle masses, force strengths whose values are just put in by hand. They have to be measured experimentally. The theory doesn't predict why they have the values they do. Adding neutrino masses requires another 7 or 8 arbitrary parameters. It feels a bit ad hoc to many physicists.
Less like a fundamental explanation and more like a really good description that needs specific numbers plugged in.
That's a fair way to put it. There are also deeper theoretical questions, like the hierarchy problem. Why is the Higgs mass so much lighter than the scales associated with gravity? Or issues like quantum triviality and reconciling the model with cosmic inflation in the very early universe.
So even with this incredible standard model, there's still so much territory left to explore. It's not the end of the story.
Not by a long shot. It's a phenomenal achievement, a testament to decades of work. But its very success, its precision, is what highlights these missing pieces and paradoxes. It serves as both a bedrock and a launchpad for seeking a deeper, more complete understanding of reality. It's an incredibly active frontier.
This deep dive into the standard model really has shown just how much we do understand about the universe's fundamental pieces and how they interact. From, the quarks inside protons to the Higgs field giving mass, it truly is a monumental achievement. But as we've explored, it's also this powerful reminder of how much more is out there, just waiting to be discovered. If this incredibly successful model still leaves us asking about 95% of the universe, dark matter, dark energy, and can't even conclude gravity yet, well, what does that tell us about the vast, uncharted territories still ahead? What fundamental principles might we still be missing to really complete this ultimate periodic table? Thanks for listening. We'd love to hear your thoughts. What do you think is the most exciting unanswered question presented by the standard model, and why? Let us know in the comments. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.